We are looking at a simulation of infinite state generation. The goal is to engineer a theoretical reality architecture from cold mathematics. Theoretical systems built to generate sequential states run into a structural failure. Unchecked expansion triggers scalar drift and infinite historical recursion. The system creates too many unique coordinates, requires too much memory to track their lineages, and eventually crashes. The Experiential Reality Machine, or ERM, provides a concrete architectural specification to address this mechanical limit. It operates via a mechanism called deterministic reconvergence. Instead of allowing numbers to drift, the ERM utilizes a non-injective rational algebra operator to force expanding pathways to fold back into one another. This framework is designed to allow an unbounded interaction space to remain self-reconciling, maintaining structural integrity as it scales. This diagram establishes the topological boundaries of the machine, a strict fundamental interval, bounded exclusively between the numbers 1 and 2. No matter how complex the internal mechanics become, every generated state is mathematically forced back into this exact interval. Beyond these mathematical limits, the ERM is built on a meta-methodology known as the epistemic firewall. The specification enforces a rigid separation between its epistemic tiers. Foundational axioms, analytic theorems, finite certificates, and open propositions are strictly isolated from one another. This taxonomy ensures that a finite computational scan of a local system state never migrates into an unproven universal analytic claim. To observe these constraints, we will initialize the model directly from its core master ledger. This visualization shows axiom 3, the Genesis vocabulary. We begin with a single Stark token pair defined by the coordinates 1, 1. The 1, 1 pair is the absolute foundational ground state. All dynamic complexity evolves from this point. To generate new states, we introduce axiom 2's interaction algebra. The function f of x and y equals n times y plus 1 over x. The raw calculation is defined by taking the y-coordinate of a given token pair and adding the reciprocal of its x-coordinate. The mathematical result of this addition produces a raw output defined as the pre-normalization sum. This algebraic interaction creates a compounding engine, allowing our ground state to generate an array of new numerical coordinates. The pre-normalization sum inherently pushes numbers higher. Without intervention, these values immediately escape our boundary interval. This issue is directly resolved by Theorem 3.3, which defines branch-specific octave scaling. This illustrates octave normalization. Raw sums scaling past 2, 4, or 8 are divided by powers of 2 until dropping below the interval ceiling. Sums between 2 to the power of k and k plus 1 are proportionally divided, snapping them perfectly back into the fundamental interval. Octave normalization guarantees that generated values do not suffer from magnitude divergence. They remain within the topological bounds. This leads to the concept of a non-injective mapping, as established in Theorem 3.2. Because of the scaling limits, different starting coordinate pairs can result in the exact same final output once they are normalized. This is a deliberate structural compression. It forces the network to fold in on itself, ensuring the machine maintains bounded complexity. We can verify this compression by examining a certified mathematical witness from the active epoch vocabulary. This diagram illustrates the proof. On the left, we secure our first certified admissible parent pair, 7/4 and 481 over 252. On the right, we introduce a distinct second pair, 63 over 52 and 139 over 84. We run the raw sum calculation. The left track calculates 481 over 252 plus 4/7. The right track calculates 139 over 84 plus 52 over 63. Both parallel tracks converge into a unified central node labeled 625 over 252. This is exact pre-normalization reconvergence. Because 625 over 252 is greater than 2, the normalization operator pushes it into the fundamental domain. Dividing the raw sum by 2 yields our final normalized output, 625 over 504. Certificate 4.1 confirms via an exhaustive depth 3 scan that exactly 2 pairs map to this specific coordinate. This algebraic collision provides numerical evidence for the ERM's many-to-one token folding mechanic. The system curtails its own expansion. Looking at the macro view of the generated network, we see multiple divergent pathways merging into single points. Because these collisions evaluate directly from the active coordinates, the machine determines current states without needing to reconstruct an ancestral lineage. By passing recursive historical lineage crawling, the architecture naturally sidesteps memory collapse. The system evaluates forward, making it inherently self-rebooting. However, the system is not amnesiac. Axioms 5 and 6 dictate specific state retention rules, ensuring the machine preserves first-generation parent provenance and bounded historical edge weights. Pairing exact reconvergence with these bounded weights achieves dynamic complexity without triggering catastrophic memory bloat. The core mathematics governing this architecture are cemented in a locked baseline, version 1.0 frozen. But the epistemic taxonomy leaves the unmapped extremities of the system undefined. They are cataloged as open propositions for future investigation. Proposition 5.1 addresses asymptotic multiplicity bounds, questioning whether collision multiplicity remains bounded as the domain expands. Proposition 5.3 investigates the existence of multi-step closed dynamic cycles within the unbounded operational envelope. The internal audit is complete. The foundational laws and finite certificates of this reality machine are settled. While the deterministic interaction rules are now a matter of record, the distribution of the image space under infinite iterations remains an open research horizon.